Hello, hello, everyone. Ladies, gentlemen, non-binary, thank you so much for joining us today. I'm Amelia Thompson. I'm your host for the Wurth Electronic webinars. And joining me once again in our very separate studios is Chem Sum, the year director for Wurth Electronics Midcom in Germany. Welcome back, Chem.
Hello, welcome.
Today Today's webinar is actually the sequel from last week's wireless power transfer webinar. Today, we are going to dive deep into the world of advanced coil knowledge. We're going to learn about advancements in coil and also their design. As a reminder, if you have any questions during today's webinar, you can ask them in the questions box. And actually, right before we went live, Chem and I were discussing how we like our coffee. So if you want to test out your own questions box, you can tell us how you like your coffee. I'm a little curious. We differ very much. Chem likes his cappuccino. I like my straight black coffee because it helps wake me up in the mornings. But yeah, you can go ahead and test it out. We have a few answers coming in. Somebody likes their lattes, caramel lattes. I do like a good caramel latte as well. I do agree with that. So again, if you have any questions, simply ask them in the questions box and Chem will answer them at the end. Because you registered for today's webinar, you will automatically receive the video on demand as well as a PDF of the slides within the next 24 to 48 hours following the presentation. Just look for them in your email. You should be receiving an email from here for you at we-online.com and register for our next webinar. We are discussing capacitors. Frank Buhani returns with capacitor selection for high power buck boost converters coming up June 9th. Register online at www.we-online.com/webinars. And of course, all of our webinars are made possible thanks to our exclusive sponsor, Digikey Electronics. All right, I'm going to go ahead, pass it over to Chem as he presents wireless power transfer advanced coil knowledge.
Thank you, Amelia, for the words, and I'm happy to be here again in my second session, and let's see we can continue our great session from last time. So welcome also from my side for the wireless power transfer advanced coil knowledge session. We cut the cord. As mentioned, my name is Chem Sum and I'm responsible for the wireless power transfer globally at the Würth Elektronik. Today, I would like to give you a short agenda, what we are going to do and what's the targets. First of all, a short reminder about my first sessions about applications where you can use wireless power transfer systems and technologies. After that, we go into the physics and have a look into the coil and materials, how do they impact your design and this coil, and the tuning for sure, how you can do this by yourself, or of course we can help you out there. Besides the consumer products, there are a lot of other and different and additional product areas and application areas. As mentioned before, in last week's session, I showed some examples also for automotive. In this picture, you can see a charging possibility for e-cars. They are transferring, in this case, 3 kilowatt power from the charging pad to the car to charging the car itself. At this YouTube video, there is a BMW marketing video which shows nice videos how this is done in the BMW. Additionally, for furniture infrastructure topics, as an example, I'm staying here in my home office. I'm possible to charge my mobile directly on the table or in the table if the charging pad is included. But additionally, you can just imagine you can do this on bus stations, in the plane, in trains, in your meeting room, or anywhere else where you are waiting or you are on traveling. Additionally, a big area, of course, is the medical technology area. For sure, a lot of topics will come up during the COVID and Corona time and pandemic, but beside this, there are a lot of other different medical products and components can include wireless power transfer technology. For example, you are having a kind of tablet which is used in hospitals and you have to disinfect them. If you have any kind of contacts for charging an USB or micro USB, it is an open point in an open part, and this will be defect at a specific point. But if you just seal them, completely cover them, and you charge them wirelessly, this will be a very long-term solution. Additionally, for industrial rough areas, as an example here, I have a picture of an agricultural robot, or maybe some submarine robots under the water. They can be charged wirelessly, or these robots, they directly send data wirelessly by GPS, Wi-Fi, Bluetooth, but the battery is the 99% will be charged by a charging station, and you have to maintain these robots. But this can be done also wirelessly if they are going to a specific charging point and do the charging and continue the work completely automatically and autonomous. As an example out of the medical area, here we have a customer of us, Cochlear, and we started with them in 2014, 2015 for this sound processor. The sound processor is placed on your head and is working with this cochlear implant in the head of the patient. So that means here, I have to point my pointer. In this circle here, we have a wireless power coil included in this housing. This wireless power coil is transferring energy from the battery, which is included in this case, to the cochlear, and the cochlear implant will send data back to the sound processor. As another example, now we go back to the consumer branch, is an iPhone. I just had a quick look into the website iFixit, where you can find very nice pictures of the iPhone 12. Why I'm showing this here is, as you can see, the coil, which is the main topic of today, you see that the Apple engineers placed the coil on the backside of this, on the cover, as you can see here. The black one, that's the Ferrite sheet. And if you just take it off, the coil here in this size. The size of the coil, as you can see, is as big as possible in the housing of this iPhone. So why this is the case? This I mentioned in my first session is that we will have a very good one-by-one effective area transmitter to receiver coil. Now let's go into the coil physics. I think that's the important point why we are today here. First of all, before we go to the wireless power coil, I would like just to make a short remembering of inductive basics. If we look into a single conductor, we can throw a current to the single conductor, and then we can see around the coil a magnetic field with the right-hand law. If we now use an air coil, which is wounded around here, and we also have a current which is flowing through it in the voltage, then we can see that the magnetic field will be focused inside of this air coil, as you can see here in the picture. And for sure, we have a stray field around. If we now place a ferrite material inside of this air coil, a rod core, all this magnetic field, the most of them, not all, the most of them will be focused inside of this coil. So this kind of, let's say, coils, or this one here, is used in, for example, in your electric toothbrush, yeah? Since, I don't know, 30 or 40 years. So this is not rocket science. But important is how you can calculate the inductance. There are main physical topics which you have to take into account. First of all, the permeability of the material. So this red part here, this is our permeability, that means the ferrite material. There are different kind of materials possible to use for. The second is the magnetic area. So as you can see here in this picture, for sure, you can have smaller magnetic areas or bigger ones. The third one is the turns. So also an inductor or transformer or any inductive product, if you have a different amount of turns, this will influence your inductance. And the last one is the effective field length. For this ring core, you can see the effective length is around this round-shaped core. So not very surprising, in our formula, we have the permeability, the effective magnetic area, the turns, and the effective length, how to calculate the inductance. So why this is important and why I'm showing this is that we will have today a closer look to the permeability, so the used material for ferrites. The effective area, this was explained in my first session, the turns for sure, and the effective length, these are given from the wireless power G specification or a proprietary system, what kind of inductance value I would like to achieve. But additionally, to mention here is the magnetic area, or let's say the length of this, for sure also depends on the size of the coil. If we now look into a wireless power transfer system, in this specific example, we have an inductively coupled magnetic resonance system. So we have on the left-hand side, L1 is our transmitter and L2 is our receiver side. Here we have the load, here we have our source and the resonance tank, which we can see here. Between these two coils, we have a coupling. This coupling is influenced by misalignment, by X, Y, and Z, by the material and how do they couple to each other, by the frequency, and for sure of the Q factors, which are directly in charge of this air gap. So that means we have this air gap and we have a transmitter and receiver side. This could be, for example, a rotating system, and we have a specific air gap D. One of these coils could look like this, for example. The system is working in kilohertz range if we have an inductively coupled system, a closed coupled system. Short range are normally working here. So we are talking about up to maximum 10 millimeters, I would say. The efficiency is a quite complex formula, but to break it down, to make it more easy, we can say the maximum efficiency we can achieve if we have the best coupling of these two coils and the highest Q factor of the whole system. So these are the main topics to get the best efficiency of the system. So a high Q factor we need for the system. How we can achieve it? Or better way, before we go to how we can achieve it, what effect we have. In this case, this is the figure of merit of efficient power systems, is that we can see as bigger the Q factor is of the system, we can see the curves here, the maximum efficiency will increase. But after the green line, you see 100 or 200, the efficiency is just increasing very incrementally, very low. But in general, as high Q coils will have then, for a good coupling, we can increase the distance between the coils, or we will have a better efficiency. And the freedom of position in between these two coils in X, Y direction will be better. Additionally, according to the quality factor, also the coupling is important. In this case, the coupling, as an example, we did a FEM simulation. You can see the transmitter here, the half of the transmitter, it's rotating, and the receiver. And if we look into, let's say, as an example, at a 2 millimeter or 1 millimeter distance of these two parts, and if we have a 0-degree angular misalignment, so they are both of them parallel to each other, then we will have, for example, at 1 millimeter distance over 0.95 percentage or efficiency according to the coupling. If we now have the same system with the same coils and we just increase our angular misalignment, then you can see that coupling will drop by 50%. Nothing is changed. The Q factor is the same, the parts are the same, the materials are the same. We are just increasing the angular misalignment. That's an important point for you as an electrical or mechanical engineer. You have to always take part with the design engineer. If your design engineer, for example, would like to make a charging pad and the remote control will be placed a little bit in an angular misalignment because the display can be read better from the customer. So always take in mind, all changes will minimize the efficiency, the coupling of the total system. As an example for the area, which I mentioned before in the formula of the inductance, also here we have the area between the two coils which are coupled to each other. I don't want to go into detailed formula here. Important is that you can see if we have a standard A10, A11 transmitter coil, and we have a 1x1 area of the receiver coil, the coupling factor is 0.8. So the areas are more or less the same. If we have a coupling, if we have a coil which is just half of the size, we will have 20% less of coupling. 20% less of coupling is 20% less efficiency. All these figures and all these data you can get in our Red Expert tool. If you just click on the different kind of transmitter receiver combinations, and then you just can filter out which combination of coil pairs are best fitting and have the highest coupling factor K. As an example, I put out here 4 of our standard products just to give you an idea of the different kind of coils on the receiver side, which are not specified by Qi, but they can use in Qi systems. As mentioned here, this is the same coil before, which we have by 1x1, for example. But as you see, the Q factor is 30. And the smaller part have a higher Q factor. This is the reason because we're using here a Litz wire and a solid ferrite. Here we have a very thin, flexible ferrite, like here ISO and here. But the Q factor, as you can see, is minimizing on these 2 parts as well, because here we have a bifilar, very thick wire. You can see it in the picture. Here we have also bifilar windings, but the RDC, you can see it here in the line, is a lot of times higher than this one. And the same for this very round shape one. All these parts are able to use with the A10, A11 charger. How this looks like and which will be now the best choice. So out of my customer view, I would say, hey, I would like to use the highest Q factor because I learned as higher the Q factor, as better the efficiency and better the coupling it is. Is this really true? Have a look at our results. What a surprise. No, we don't have. You can see here the blue line. The blue line is the biggest coil with a 207 in the end. So the part which don't have the highest Q factor will have the highest coupling factor because of, as you see, the Q factor system will be calculated. And why this is the case, but they have the highest coupling. It's not only the quality factor influencing the whole system coupling, it's also the area of the 2 coils which are penetrating the magnetic field. As smaller the receiver coil according to the A10 coil in this case, as smaller the coupling factor it is. It doesn't matter that the Q factor is higher here. The total FOM value is smaller, as you can see, as we will multiply them by the coupling factor. So you can see that not only the quality factor is important, also the area of the coil itself. And as smaller the parts are being, as smaller the coupling factor will be, according to the big one, and the total Q factor multiplied by the coupling is also smaller. Now let's have a look. If you have a proprietary system, not a Qi transmitter and Qi receiver, and you want to use maybe the same size coils on transmitter and receiver side, which is possible. As an example, I choose 2 rectangular shapes and 1 round shape coil, which are coupled with the same A10 coil from before. And here we see more or less all of them are in the same area at example 6 millimeter. As you see, all coils have high Q factor. This is because we are using Litz wires with high amount of strands and a solid ferrite with a very high high permeability factor. And as you see, they all have a very good coupling factor, and total FOM numbers are also very high. So with these solutions, you will have a better efficiency, a better coupling, and a better power transfer system. Now let's go to the material, to the ferrite material impact. We just have now a look onto the wires and how do they impact the Q factor, but also the permeability have an impact, as we remember to the first slide that the inductance will be calculated by the permeability mu. But how this looks like, first of all, in our simulation. If we have an air coil, we just have a magnetic field around it. So there is no shielding and it's completely around the air coil. If we now place a ferrite shield on the backside, the magnetic field will be focused inside the ferrite material and then will go up over our coil. So the air coil is placed for sure on top of the side. If we now have 2 wireless power coils, so like a transformer with a big air gap, the transmitter and the receiver coil, they will focus the magnetic field between these 2 ferrite plates. So this is a focus, and so we will have better efficiency, and around these 2 coils, the magnetic field will be very, very low. Out of our book Trilogy of Magnetics, here I have a nice curve of different materials which can be used. I initially mentioned that magnetic zinc, nickel zinc, or just iron powder, for example. As you can see, these curves will show the impedance curve according to the frequency. And iron powder, as an example, the black one, is usable up to let's say 10 megahertz maximum. Over that it will have no effect. In red, the magnetic zinc cores, they have a higher frequency range. They can be used up to 100 megahertz, for example, or maybe 80 roundabout, and the losses rising above 10. As you can see, above 10, the curve is dropping down. And also here you can see more or less after 50, 60 kilohertz, the material is dropping. For the nickel zinc materials, which used for higher frequencies, they are dropping down after 20, 30 megahertz, and it's possible. But now, which material should I use for a wireless power transfer system? So in general, we are using nickel zinc or magnetic zinc materials. As you can compare, the permeability is not always the biggest decision maker for us. For us, it's more important about the power losses. So we need power losses which have a low value at a range of 25 to 150 kilohertz, 200 kilohertz. So as you see here, for example, the value is 400, or here it is less, it's 125. So these 2 materials we can compare, and both of these materials we can use in our cases, as the permeability, initial permeability value of 800 or 2400, yes, for sure, this will help, but there is no big step in the inductance or Q factor between these two materials. More important is to use low loss materials at the working frequency. So how we can compare these kind of data sheets? For an example, for the mu prime and mu double prime, you can see in this both charts, as you see that we are in the megahertz range here, and we are working in this low field of 100 to 200 kilohertz in this end, as you see also on this side. So that means the mu prime should be stable over the range of this working frequency, which is very good on both materials. And the mu double prime, which will cover the AC losses of the material, should be as low as possible. Yeah. So if they are in this more or less 0, but it's 10 range, and also here in this range, that means for our side, the losses of the material, the AC losses of the ferrite material are very low at our working frequency. These data are from our ferrite manufacturer, Acme. As an example, we have a wireless power transfer system used on a G reference board from Texas Instruments. It's a A11 design. On top, we placed different receiver coils with different materials and measured them on the back side. What can we measure? And we measured on the back side different curves of the harmonics. And these are very important if you would like to get the certification for EMI, so like CE, FCC, and this is very important. And if you would like to place parts of PCB on the backside of the receiver coil, for example. And you can see the best performance we have with the magnetic zinc material, this black one here, this is the red curve, as this material have in this case the highest permeability. So this is the material with, let's say, more than 2400 permeability, initial permeability, and this solid ferrite, it's the blue one, the permeability here is around about 800, which we have seen before. And this is an additional part which is using this iron powder. So as you see, the permeability here is much, much lower. And so the harmonics, so the first one is much higher, the peak as, for example, with the highest permeability, which does not mean that the Q factors will differ a lot. They could be all in the same range because the Q factor also is influenced, as mentioned before, from the wires. We do an additional 3D FEMM shielding measurement, or let's say simulation and measurements. And as you see on the backside of a round shaped coil with these dimensions, that on the backside there is no field, as mentioned before. But a lot of applications need a hole in the middle. I don't know if you want to place it on your smartwatch and you would like to place a sensor in the middle, or you're using it in any kind of rotating systems, for example. But you cannot make a hole in it and then don't expect any magnetic field on the backside. As you see here, the hole in the middle is not mentioned here, but the hole in the middle is around about 2 centimeters, and the magnetic field will come back on this side. If you just go back by side, you see the magnetic field is completely focused on the top side, and here you can see that we have a significant field on the back side. Now also some kind of applications want to have, instead of a full plate like this, to minimize the weight, we can use just stripes. Also this kind of stripes, if you see here is an example that the inductance with the hole is more or less the same without hole. If we now go to the stripes, you can see a drop of the inductance as we have less ferrite material with permeability, and you can see it's possible to be in the range, maybe it's 20% less of the original one, but also here we can see much more magnetic field on the backside, which means you need for this kind of material or which kind of application a shielding material or a bigger distance to your PCB or the rest of your circuit. Also, there's a big difference if you look into this cutting, or if you look into this way. As you can see here, if we are not over the ferrites, the magnetic field on the backside is much worse. As mentioned before, the wires are also very important. We are using different kind of ways to build up the wireless coils. And as mentioned before, we have as a simple solution, very cheap, it's a single wire. Could be different wire gauges, millimeters, square millimeters, and to thicker ones, as you can see here. And also we can do bifilar or trifilar windings to increase the copper cross section, but the height will be the same. Or we directly go to the Litz wire to increase, to reduce the skin and proximity effect. It is also more flexible than the wire itself, for sure, but it's more costly. To increase again or decrease the RDC, we are using, for example, also bifilar Litz wires. So we just glue them together and make the winding. And here again, we are reducing the skin and proximity effects, using the same diameter of the coil, but we have more copper cross section, and this will reduce the RDC again, but for sure, the costs are getting up. The coil tuning. The coil tuning itself, it's also a quite interesting topic. So the first of all, yes, we do coil-specific solutions. For this case, just get in touch with us, fill in the inquiry sheet, or directly contact your local Würth Elektronik sales contact. In this inquiry sheet, I just want to go very shortly in this. We need initial information about the electrical parameters and which area we are talking about, and some mechanical thermal specification that we know in which range we are and if we are capable to produce it. To optimizing the coil, as mentioned, the coil tuning, what are the main factors? First of all, use the largest possible coil in your application. As mentioned before, at the iPhone also they are using the whole area on the back side of the housing. Keep the distance in the range of the maximum efficiency. As you have seen, we have different distances, and different distances will have different coupling and different efficiencies. If the misalignment is also low, like in X, Y direction or in Z direction, the coupling is better, and that means again, for sure, a better efficiency in the end of the day and will increase your whole system efficiency. Choose the best matching coil, which can be helpful. In our tool Mix and Match at our website, you can find the coils out of our portfolio which are matching to the best and will help you to find the best combination. The parameters, for example, the FOM, will influence the performance. So that means it's very important. You cannot change just from single wire to Litz wire, or from a nickel zinc to manganic zinc. It's not a super high difference, but also there is a difference about this. And if you would like to have it a very flexible part, for example, and the material, the iron powder, will have a lower permeability, and then in this case, your performance will be lower, or you have to make it thicker or bigger or what else. Our products, as mentioned, we have the broadest portfolio in the market and of standard parts, but as mentioned before, we do also customized solutions from very small parts like 6 millimeter diameter up to very big ones like this one for up to 100, 200 watts proprietary solutions, or you're using standard parts like we see here in the picture for A11, A10 chargers for the WPC G specification. In the end, just want to give you some information about our website, where you can find a lot of informations and FAQs and design kit informations, where you also find the inquiry sheet for the custom coil solutions is here. Also, if you would like to get some reading materials, we have our trilogy. So out of my shelf, yeah. Also here you can see the book. A lot of informations are here inside for sure. Also the basics, which I mentioned before, as an example, the skin and proximity effects are also explained in this book. In the end, thanks a lot for your attention, and I hope there are some questions, maybe feedbacks about your coffee for sure. And I'm happy to answer all your questions. And Amelia, I will take over to you.
Okay, outstanding. Thank you very much, Chem, for presenting today. We do have some questions coming in, and you briefly touched on this at the end, but do you have any other writings regarding wireless power?
Sure, we have. On our website, you can find a section for application notes. And right now, I think we have 4 or 5 different ones from basics and advanced coil knowledges. Also, our newest one, which will follow up also in June, we will have a webinar according WPT, wireless power transfer, including NFC data communication. There's also an application note, which is quite new. So yeah, I think there are a lot of writings you can find on the website.
Yes, absolutely. And we can make sure that we include the registration link to June's webinar on wireless power and NFC technology. We're very excited about that. Our next question, how do you define the Q factor? And do you have an equation?
Yes, for sure. Also here again, in the book, you will find the equation and equation for that. So the Q factor, you can directly calculate, and the formulas you can find there. Maybe I can, by chance, I can find it out. And the important is here, the Q factor is a calculated value, which is depending on the AC resistance value. And let me see, I can find it out of my head. The Q factor is here. Anyway, have a look on the book. I have it not in my mind, but yes, there is an equation. That's the answer.
Thank you. Our next question, is the Q factor here for the single coil shown, or is it for a pair of coils?
That's the pair of coils. So it's a transmitter receiver coil. So maybe I was too fast in my on my slide. It's always the transmitter and receiver coil combined is the whole system Q factor, which will influencing, or let's say, which will give you the whole quality factor of the system. Plus, you have to multiply it by the coupling factor, which will affect the FOM value.
Thank you. Our next question here, which of these ferrite materials has less tolerance to temperature changes?
Good question, Mary. So according to temperature and the ferrite materials, how do you say like that? As an example, if you have a ceramic part, I don't know, like plates or something like this, a ferrite is also a ceramic material. So you can heat up a ferrite material up to, I don't know, super high temperatures, because they will be burned in the factory at 1000, 1200 degrees Celsius. But the tolerances for sure depends on, let's say, what are the mixture inside the ferrite material, the granulates. So normally there is a defined working temperature range, depends on the mixture, what is used at manganic zinc material, for example. And then the tolerances are given in the data sheet of our parts, but additionally of the ferrite manufacturer. There is no, let's say, thumb values where you say just, I don't know, 5% or 10% or something like this. It depends on the ferrite material mixture, and the used temperature range could be up to 90 degrees, could be 150, or just up to 40. So it really depends on the material mix.
Okay, thank you. Our next one, I can actually answer this one. It was asking if the presentation will be available in 2 days. It will be. It'll be sent from here for you at we-online.com, and it will be sent to the email which you registered for the webinar. So be on the lookout for that. Our next question, is it important to increase the inductor value of the coil if you want to develop a higher power system?
No. So the answer is clearly no. If you want to have a higher power, the only, let's say, what you have to adapt is the copper cross section, as you have to drive a higher current or a higher voltage anyway to get a higher power transfer system. If you would like to drive higher current, you would need a bigger copper cross section, which means you need to have, as an example, a Litz wire or a bifilar Litz wire or thicker Litz wires to minimize skin and proximity effects. But the inductance could be the same because you don't change the turns, you're just changing the wire diameter. And for more power, I absolutely suggest to use Litz wires.
Okay. Next question, we are winding down. Is it a good idea to do winding as a PCB trace?
Yes and no is the answer. So the why it's good, if you have, for example, power transfer systems up with some milliwatts, microwatts, or maybe up to maximum 1 watt, so like also which is used in the NFC standard, then you can do it with PCB tracks in your directly. If you're going over 1 watt, I would say, or maybe 2 watts, maybe also possible, you need a bigger copper cross section, because then it's maybe also possible to do in the PCB, but skin and proximity effect again here will increase the losses in your PCB, and then it's getting hot, and you don't want to have the eddy currents on your PCB, I'm sure, if you're working in these kilohertz ranges. So at higher power, I would absolutely suggest using then wire wound coils, Litz wire coils, which will minimize your losses and the heat dissipation on the board.
Excellent. And our final question here, and just a reminder, if we do not get to your questions, we will answer them after the webinar. Again, we'll just email you and make sure that everybody's email is or question is answered. For certain specialized applications, is it possible to pot the coils with epoxy? And if so, what type of epoxy material would you recommend?
Also, this is a very good question. In principle, yes, it's possible to pot the coils. Important is that the temperature during the potting, as mentioned, the coils are they're glued to the wires are glued to each other during the winding process. So if you do a potting or injection molding, for example, you can do that. You have to do it as fast as possible, and yeah, you don't have to move them because they have to stay in that. And which kind of epoxy material, this depends on your application, I would say. What is needed, best case, no metal inside it, yeah, because all metal will shield your coil, and then wireless power is not possible to do. So I would say there is not an answer, use this and this. So in principle, you can use all epoxy materials which you would like to use in your application for that temperature or for this, I don't know, application or board or product, but no metal must be inside it.
Okay, well, that ends our webinar for today. Cem, thank you so much for presenting. We really appreciate it.
Thank you so much, Emilio, and enjoy your time.
Absolutely. And for everybody who has joined us today, thank you for hanging out with us, discussing coffee and wireless power technology. Don't forget to register for our next webinar. We're taking a week off, but we are coming up June 9th. It's capacitor selection for high power buck boost converters. Frank Buhani returns with that on June 9th. Register online at www.we-online.com/webinars. I'm Amelia Thompson. Thank you for joining us today.